What I wanted to talk about today is obviously neural electronics and give a particular flavor. We use organic electronic materials, and I will justify why we do that. Um, Let me start with an observation that neurological disorders is the leading cause of disability. According to a study that looked at numbers up to 2016, there are 276 million disability adjusted life years, or DALYs as they're known in medical language, in 2016 because of neurological disorders, with stroke leading the way, and then other disorders as indicated here. So this represents a major societal challenge that drives a lot of the work in this field. Um, More importantly, there is this observation which is called Irum's law, and Irum is Moore's law spelled backwards, that postulates that the discovery of new drugs is slowing down and it's getting more expensive with time, which is the opposite of what Moore's law postulates for electronics. So this points to a grim reality that drugs are not going to provide the answer for the burden of neurological disorders. The good news is that there is this new field that it's emerging called bioelectronic medicine that has the potential to provide a game changer in this field. One example shown here is deep brain stimulation, where you have electrodes implanted in the brain. And through electrical stimulation, you can ameliorate the symptoms of neurological disorders, movement disorders initially, such as dystonia, Parkinson's, tremor, symptoms of epilepsy, but recently expanded to psychological disorders such as OCD, depression, and even disorders such as obesity. This is something that dates back to the development of the pacemaker in the late 50s, early 60s for the first fully implantable devices. And then we had a decade later cochlear implants for restoration of hearing. These devices are now fairly commonplace, with pacemakers being implanted at the tune of 600,000 per year, and hearing implants at the tune of 35,000 per year. And similar numbers are for spinal cord stimulators that are implanted on the spinal cord, as the name says, for ameliorating the symptoms of chronic pain. This is forecasted to grow quite a lot with the opioid crisis. Then later, you had vagus nerve stimulation for epilepsy, sacral nerve stimulators for bladder control, deep brain stimulators initially for movement disorders, and then extending to other conditions, retinal implants, implants for sleep apnea, and what is called electroceuticals, or stimulators for the peripheral nerve for autoimmune diseases. And this is not a comprehensive list. It actually takes off at a very steep rate, almost exponentially, with more and more devices coming up as time progresses. And the field has attracted commercial interest even from entities that you would not associate with bioelectronics. There was an alliance between a pharmaceutical, GlaxoSmithKline, and Google's parent company, Alphabet, a couple of years ago, that gave rise to Galvani Bioelectronics. Then Elon Musk got into the game, Mark Zuckerberg. So there are high expectations, which can be good or bad. Investment in the field, of course, is wonderful. It's great to be working in a field that's very hot. What you want to make sure is that there is some staying power and some good things happen out of this commercial interest. Otherwise, the whole field will be hurt. This technology is very promising, but has some severe limitations. We do not, first and foremost, we do not understand how the brain works. The brain is a very complex machine consisting of upwards of 80 billion neurons. And although we understand how neurons communicate with each other to a fairly good extent, what we do not understand how this communication gives rise to behavior. It's something that's currently beyond our knowledge sphere. We can study this this process, and this is done in the clinic by using different electrode configurations, going from scalp electrodes that are non-invasive but probe a fairly large area of the brain with many, many networks of neurons, all the way to the other extreme where you have penetrating probes that are obviously highly invasive to the brain, but they can provide very high quality information. If the electrodes are small, they can pick up single units. Intermediate between the two is cortical arrays that sit on the surface of the brain. This is for recording these configurations and for trying to understand how the brain works, but then you can turn it around and ask the question, how does it work when I modulate now the brain by applying electric fields? That's also something that's not understood. We saw a video of a patient whose tremor disappeared to a large extent when the stimulator was turned on, but we don't understand this process. This goes hand in hand with limitations in technology. The signals that we're trying to detect are small and complex. The in vivo environment is hostile to traditional electronics, and traditional electronics are highly invasive and often require multiple surgeries to replace, for example, batteries or corroded leads. And this is something that obviously patients do not like. And the technology limitations and the fundamental limitations in our understanding of how the brain works go hand in hand. If we improve technology, we'll improve on our understanding of the brain. So we're at this point in time where new technologies are needed in order to address these limitations, both very practical ones and more fundamental ones, and enable this wonderful field of bioelectronic medicine. So what I wanted to do today is to convey our enthusiasm about three such technologies. One that uses mixed electronic ionic conductors. These are materials that are able to transport both electronic carriers and ionic carriers. And as such, they improve the coupling between the biological system and electronics. And I'll show you some work on cortical electrodes and then on transistors. The second technology is electrophoresis, which is the process of transporting an ion through a solid state material, in this case, by applying an electric field. And we use this to deliver drugs in the brain under electrical control. And I'll discuss the merits of this approach. And then I'll talk about some devices that change shape and they can decrease the invasiveness of neurosurgery. We take a broad view of what bioelectronics is, and we view it as the interfacing between biology, living systems, and microelectronics. And again, the justification can be a more general justification, can be that microelectronics represents the most sophisticated technology that humankind has developed. And we want to use this technology in order to, A, understand how biological systems work by using microelectronics to sense properties of biological systems, but also use it to actuate and trigger processes in the biological system, leading to new treatments. In our mind, this is an exercise in drawing bridges among properties that are very different. If you look in this slide, you see that a typical PCB board is mechanically stiff, made out of materials that are mechanically stiff, while tissue, especially the brain, is very soft. So you have a mechanical properties mismatch. There is a communication mismatch as well. These two components will communicate by exchanging an electric current, while the communication of cells, tissues, organs here is very complex and takes place at different levels, from very simple, using messengers that can be as simple as small metal ions, all the way to components of cells or multiple signals being broadcasted at the same time. Biological systems are dynamic, they evolve as a function of time, while in their traditional form, electronics are static. So this is fabricated and spends its life in this form. So what we try to do is to bridge the two properties. I'm not going to talk about the mechanical properties mismatch. This has been addressed by the community to quite a good extent. And in our work, we pay a lot of attention in the communications gap, trying to get electronics to speak foreign languages, to be able to communicate with signals, including ions and more complex biomolecules. So I'll show you a couple of examples of that. A motivation for the early work in our venture in bioelectronics was epilepsy. We were working closely with an epilepsy group where they care for patients with drug-resistant epilepsy. And this represents about 30% of people who suffer from epilepsy, plus epilepsies that were very severe and were disabling to the patient. So in that case, resective surgery is the next treatment option, where the patient is brought in, electrodes are implanted at different parts of the brain, different locations of the brain, and the activity is monitored as a function of time until a seizure manifests itself. And what the neurosurgeon is trying to do here is to figure out which part of the brain has given rise to this seizure. And often the dilemma is this the right area, or did the seizure really start here and then it propagated to this area and then to that one? So to help answer this question, better recording technologies are needed. Also, it would be great if you could look deeper in the brain without having to penetrate it from the surface. So these two challenges motivated a lot of the early work. And one early observation was that if you want to improve the coupling between the signals in the brain and electronics, you need to look at how an ion in an electrolyte couples with an electron in a semiconductor. Now, if you try to do this with silicon, which is the obvious material in microelectronics, you run into quite a few issues. First is that silicon is not stable in biological media. It actually etches at the rate of a micron a month in cerebrospinal fluid. And so you need to have an oxide or a nitride that will protect it. And this spaces away the two carriers, decreasing their interaction. Even if you get away with a noble metal, for example, that doesn't have this barrier layer, you're going to end up in a situation where you have ionic carriers on one side of the interface and electronic on the other, giving rise to a coupling that's determined by the double layer capacitance and has a fixed value of 1 to 10 microfarad per square centimeter for pretty much any flat, impenetrable to ions electrode. Now, you could try to cheat and roughen up the surface by using nanomaterials approaches. And this has been very successful in increasing capacitance per unit area. However, there is a bit of reticence from the medical community towards the translation of nanomaterials until safety is thoroughly investigated. There is evidence that in some of these materials, there are chunks of material that end up transferring to the brain. We take the approach of using volumetric ion conduction. So we use organic semiconductors such as the one that is shown here. I'm not going to go through details of chemical structure. Just consider this as a chunk of material into which ions can penetrate and couple with electronic carriers. So you have a situation which is schematically illustrated here, where the coupling now is not along 2 dimensions, but rather volumetric. And this can help to improve the coupling between ionics and electronics per unit area. Understanding the physics of this phenomena is something that is very important, obviously. And we don't have the appropriate language. Those materials, those interfacial phenomena, if you wish, are discussed with the language of electrochemistry, which has limitations in describing the electronic device part of the equation. So this is an area in which we do some work trying to develop the language from the other side, coming from a solid state physics point of view. And we recently produced a roadmap, if you wish, for the developments that need to happen. Now, once you have this volumetric capacitance, which manifests itself by a capacitance that scales as a function of thickness, you can have stronger coupling between ionics and electronics. Your figure of merit is no longer capacitance per unit area, but capacitance per unit volume. And you can calculate that for this material that I showed you earlier, if you have 130 nanometer thick film, you end up having an apparent capacitance per unit area that's 2 orders of magnitude larger than what you would have from a platinum electrode. As a result, this means that you can make electrodes now much smaller and still record with a decent signal to noise ratio. So you gain in spatial resolution. And we took advantage of that, microfabricated these coatings on microfabricated electrodes that were deposited on a very thin polymer structure, that it gave us good conformal contact with minimal mechanical loading on the brain. So this can conform very nicely to radii of curvatures that are considered important for getting, for example, into sulci in the brain. And when tested on the cortex of rats, they were found to show evidence for single neuron recording, which is something that was not done before in the cortex, simply because people were using larger electrodes. They had given up on picking up the activity of single neurons, as these signals, when they emanate at the surface of the brain, are rather small. This is a technology that Dion Kodagoli, now at Columbia, translated to humans. And this is used to record both local field potentials as well as single neuron activities. A frequently asked question is, what is the stability of these electrodes? And what I would like to have, but we do not have currently, is a way to accelerate the testing in a way that remains biologically relevant. We don't have that. As a result, the best we can do is to implant in an animal and look at stability. And that has been done for, again, Dion Kodagoli has reported stabilities in that context. We have used these electrodes in cell culture media enriched with proteins, and we see stability for 4 months in impedance, which paves the way for pretty much all in vitro applications of this technology. Let me move to the second application of mixed conductors, which is in looking at amplifying transducers. The idea is when you do neural recordings, and this is a very simple context, you record signal and other activities that you don't care about, which we'll term biological noise. And then on your way to the amplifier, you pick up some noise because this line acts as an antenna. And then you amplify all of those. And that degrades your signal to noise ratio, this additional noise, which is significant in a practical setting. So the simple idea is that if you bring the amplifier close to the recording system, you amplify signal and biological noise, but do not amplify this line noise, so you end up with a higher signal to noise ratio. This and some other properties of transistors have motivated work by people, including Peter Fromherz, to use transistors as transducers of neural activity. And this is one example of work in this field, where they grew neurons in culture on high quality, high performance silicon transistors, and recorded neural activity, inferred neural activity by looking at the current that flows in the silicon channel. And again, in this situation, you have a coupling between ionic carriers on one side of the interface and electronic inside silicon. However, this coupling is mediated again by the oxide or the nitride that you have here. In the 80s, there was a new type of transistor that was developed by Mark Wrighton at that time at MIT that involves organic semiconductors in intimate contact with an electrolyte. And if the semiconductor is such that allows ions to penetrate through its volume, then you can have operation in what is called the organic electrochemical transistor regime. This is a terrible name, unfortunately, that stuck. A better name would be a bulk field effect. So rather than having a field effect transistor where the action is across an interface, along an interface, here you have ions that penetrate throughout the volume and couple electrostatically with electronic charges in the whole volume of the film. Again, I want to paint this with a very broad brush and not go too deep in details. We spend a lot of years trying to understand the operation of these transistors and how to tune them. And the main outcome is that you can have very large transconductances. For example, as shown here, the transconductance being the property that defines signal amplification. So when a neuron fires and changes the local voltage that is at the channel of the transistor, this is transduced into a change in the drain current. And a high transconductance means this transduction happens very efficiently. So all things being equal, this is a transistor with a 100 nanometer channel, and it operates more efficiently than a silicon transistor of the same dimensions at that time. So here are recordings with an electrode, and this electrode is optimized. It's a state-of-the-art P-dot electrode with this contact that couples electronics and ionics very well. And the transistor of similar size, the transistor showing a better signal to noise ratio, because again, it doesn't amplify the noise. And how much better will depend a bit on the setting of your system. But for a typical system, you do have usually something like 20 decibels improvement. These are recordings of activities that originate for a bit deeper in the brain. Sorry, I didn't mention, these are recordings of cortical seizures in a rat model for epilepsy. Here we're recording activities with a transistor that sits on the surface, an electrode that sits on the surface, an electrode that is implanted deeper in the brain. Obviously, this records with the highest signal-to-noise ratio. What I'm showing here is the time frequency analysis that show the frequency components in this signal as it flies by. And this is a good recording. On the surface, the recording is of much lower quality because, again, the signal spreads and you have less sensitivity, while the transistor is able to recuperate quite a lot of that loss. So it shows that you can start looking deeper in the brain when you have a better transducer. Now, an interesting feature of these devices is that the amplification scales with the thickness of the channel. The thicker you make your P dot layer, the higher the coupling between ionics and electronics, the higher the amplification. And there's really no limit at what values you can reach. Magnus Berggren in Sweden has demonstrated transistors with a transconductance of a Siemens, which is unheard of for such a small device, by making them just very thick. However, this doesn't come for free. You have to pay a price that the transistor gets slower as ions now have to penetrate through a thicker film. But this represents an interesting way to navigate the trade-off between amplification and bandwidth. As shown here, these are two transistors, one with a thick channel and one with a thin one. The thick one shows higher transconductance, but a smaller cutoff frequency. You can extend the frequency range by making the film thinner, but then you take a hit on the transconductance. So depending on what activity you want to record, you can tune your transistor characteristics. I want to put in a plug here for work by the group of Dion Kodagoli at Columbia, who has managed to extend this trade-off quite dramatically by using pockets of ions inside the P.PSS film. He calls this internal ion-gated transistors. And as a result, he can get ratios of transconductance to response time, or products of transconductance to cutoff frequency, that are dramatically larger than what you would get with traditional OECTs. So you can get very high transconductances, even at frequencies that allow you to record single neurons very, very accurately. One last thing here. This is very recent work. We started looking at how noise scales in these devices. And interestingly enough, the thicker you make the channel, not only you get access to higher transconductance, but also the relative noise decreases. And this means that you can, as you make the channel thicker, you end up having higher amplification, transconductance increases, but also you can resolve smaller minimum voltages, which is a wonderful property for a transducer. You're still limited by the fundamental trade-off where the thicker you make it, the lower the cutoff frequency. But the good news is that their noise characteristics improve with thickness. Now, let me switch gears and pass to the second application where so far we've been using mixed conductors to record ionic signals efficiently. Now we're gonna use electrical actuation to deliver biomolecules. And the context here is also epilepsy. As I mentioned earlier, the first line of defense is anti-epileptic drugs. However, in cases of drug resistance or in cases of severe side effects, and when epilepsy is disabling, resective surgery, where the epileptogenic zone is localized and then resected, is the next treatment option. However, this resection is not always possible. In about 30% of the candidates for this operation, it's not performed because the epileptogenic zone overlaps an area of high functionality in the brain. So what we advocate here is localized drug delivery with an implantable device with good spatiotemporal characteristics. So you want to deliver the drug where it's needed, just in the epileptogenic zone, and when is needed, just before the seizure. Um, what we have here is a device that's past the blood-brain barrier, and as such, it allows you to use a much larger gamut of drugs that would not pass the blood-brain barrier or would be toxic under systemic administration. So this is a very, very interesting proposition. Now, delivery past the blood-brain barrier has been quite extensively studied in the case of brain tumors, where post-resection, you want to supply localized chemotherapy to get rid of the remaining cancer cells here. There are several approaches. One of the most promising one is to use convection enhanced delivery, where you have a catheter and you push a solution of drug to kill the remaining tumors, cancer cells. However, there are many reasons why these technologies are not applicable for epilepsy, and quite frankly, they don't work well either in the case of brain tumors. So we were very excited when we saw this work from the group of Magnus Berggren and Agneta Richter-Dalfors, who developed a device they termed the organic electronic ion pump, which uses electrophoresis. That means you apply an electric field across a solid layer, which is an ion selective membrane that transports ions from one reservoir and releases them in another. And the important thing about this technology is that it provides dry delivery. You're pumping only the ion and not the solvent. So compared to convection enhanced delivery, it has a major advantage that it only delivers the drug and doesn't raise the pressure at the delivery point. So it doesn't cause edema or reflux. This was a device that was tested in guinea pigs to modulate hearing by sourcing acetylcholine. Now, the way this process works is you use an ion exchange membrane, which is a polymer that has fixed charge. If you want to use a cationic drug, you would take a membrane that has fixed anionic charge and then load your source with a solution of your drug. And again, the drug here would be the cation, and apply a potential. And what this would do is you would be able to transport the drug through the membrane, but at the same time, block the opposite side ion from going through because of this immobilized anionic charge. This is called the Donan exclusion, and it's well known in the field of ion exchange membranes. So we developed a device that uses a microfluidic to bring a solution of drug close to the area where we want to source it, and then use this ion exchange membrane to cap holes that we poked in the microfluidic. And by applying a potential, you can then take the drug from inside and deliver it to the brain. This is how the device looks in rodents. So there is a U-shaped microfluidic that circulates the drug solution. There are holes that are capped with the ion exchange membrane, and by applying a potential, we can effectuate the drug delivery. And there are electrodes here. You can sensorize the device to look at the environment into which you deliver. We use GABA to as a proof of concept. It's an endogenous neurotransmitter of the nervous system, and it represents the brake systems, the brake signal for neurons to stop firing. So here you see that by applying just half a volt, you can increase by several orders of magnitude the local concentration of GABA next to the device. And we use this to demonstrate that you can stop or even prevent a seizure in an animal model. So here we kindle the seizure, and then it manifests itself when the device is not turned on. Here we let it manifest, and then we turn the device on, and the seizure goes away. The spikes here represent to an artifact that we pick up from the electrodes because of pulsing the delivery. And here we start the delivery of GABA, try to kindle the seizure, but the seizure just doesn't manifest itself. It manifests itself a bit later when you stop delivering, if you try to kindle it again. So we only have a transient effect with these devices. Now, in epilepsy, there are dramatically different parameters that you have to use for the device, because the treatment scenario is different than in the case of brain tumors. For example, you're looking at treatment for the life of patient as opposed to several weeks, and volumes that are very small compared to centimeter scale voxels for brain tumors. So we spend a lot of time trying to understand the details of the physics by using a console model and looking at different parameters such as amount of drug that's transported, the efficiency of pushing drug into the brain versus pulling ions from the brain into the device, on-off ratio and all that, and optimize them for different scenarios. Currently, most of our work is focused on delivering chemotherapy to brain tumors. And the biggest challenge there was to make the devices produce plumes of drug that are centimeter scale. And through this optimization process, we're now able to do that. And I'm very excited about this work. Now, in the last 5 minutes, let me switch gear again and show you a final little application that has us very excited. I showed this slide before, and I mentioned, I gave a couple of examples of how we're addressing the communications gap. But what got us thinking a while ago is the difference in the dynamic properties of biological versus electronic systems. And we wanted to mimic that using electronics. We want to make electronics that can evolve or change shape or move. And as a first approach, we thought we'll make electronics that change shape and thereby minimize the invasiveness of surgery. This is what is required to place a cortical implant. It requires a craniotomy and then cutting of the dura. So it's quite an invasive surgery. Similarly, to place an implant in the spinal cord, laminectomy is required for a paddle electrode, which is a very brutal surgery. So using microfluidics integrated with flexible substrates, which is something that we learned to do for the ion pumps, we started designing devices that can either unroll or expand in a lateral fashion by simple pneumatic actuation. So these are paddle electrodes that can be rolled and then inserted into the spinal cord using a spinal tap, and then expanded by simple actuation with air or a liquid. These have been tried in cadavers, and they've been shown to expand in the epidural place in a spinal cord, and even in the brain. This is a device that has 2 radio markers on either side, and it's shown here to expand by 2 centimeters over the cortex. So the ramification is that rather than doing a craniotomy, you can envision a future where you do a small burr hole, insert the device, and then unroll it to cover a large area of the cortex. So with that, I wanted to go back and stress the point that implantable electronics, or bioelectronic medicine as it's now called, holds considerable promise for not only for understanding the brain, but for addressing neurological disease. I showed you mixed conductors that can enable high resolution cortical recordings. and also transistors with record high signal to noise ratio. We talked about electrophoretic delivery devices that effectuate drug delivery, and as a result, they represent a very good solution for inside the brain where you cannot afford to increase the pressure, hydraulic pressure in the brain. And they were shown to stop or prevent seizures in an animal model. And then we talked about microfluidics as a way towards implants that change shape. This is the group. I want to thank all of them for their hard work, collaborators at Cambridge, elsewhere, funding agencies. And again, thank you very much for the kind invitation. I really appreciate being given this opportunity. And I'm ready for questions. Thank you for your attention.
Thank you so much, George.
Thank you.
I think many people are applauding, but they're muted. So I'm applauding, I'm showing the sign. There are many questions from the audience.
I'm Professor Prashant Sonar from Queensland University of Technology, Australia. Josh,
what time is it there for you?
It is 2 o'clock.
Sorry to have you stay up.
No, it's okay. All right. I was kind of very curious about your recent development and what new things you have been doing in bioelectronics. So really impressed with your wonderful lecture. George, I have a question in terms of the like transconductance. I mean, as you know that in case of the organic semiconductors, we do have a kind of, the normal conductivity comes from the charge transport. But in this case, like we do have also P dot PSS type of material, which has ionic conductivity. So, I mean, the whole organic electrochemical transistor field where the transconductance is a function of measure of the charge transport as well as ionic, or how we can distribute them?
Yes, so the transconductance is defined as you know, as the change in current per change of gate voltage, and the drain current is electronic. So the only difference between a traditional transistor is that a field effect transistor is that rather than having all the action take place along an interface, here it takes place in the whole volume of the field. So it is really a field effect transistor, just the capacitors are distributed throughout the whole volume of the film. Now, when the ions penetrate into the film, they couple electrostatically with electronic charge, but also affect as a second order perturbation, if you wish. They affect mobility because of they affect sometimes in some materials the microstructure, but also because you are changing quite dramatically the density, the local density of electronic carriers. You move the Fermi level inside the band, so you access different densities of states. And as a result, the mobility is strongly dependent on the amount of ions that you put in the channel. So that is reflected in the fact that the transconductance as a function of gate voltage has a bell-shaped curve, as opposed to having a flat response, as in transistors where the dependence of conductivity on doping is not very strong.
Yeah, thank you so much, George.
Very welcome.
So my name is Faryad, and I'm a PhD student in Simon Fraser University, Canada. So I have a few questions. So I really enjoyed your talk.
Thank you.
Did you try some other polymers like conductive polymers, like anilines type things?
Yes.
And also, did you try to make some nanostructure of these polymers, so which like are in wire type or rod type, and they have also porosity and can help to release drugs selectively, even by applying some potential? So I'm just curious to know your thoughts on this one.
Yeah, so there is scope for developing new materials, and we've been working with Ian McCulloch to test some, among other people, to test some new materials to make better electrochemical transistors. In terms of conducting polymers, broadly, there are three families of materials. You have maybe four. You have polyacetylenes, which historically were the first, but are not stable. Then you have polypyrroles and polyanilines. However, these have this deprotonation reaction that takes place, and give very complex responses to electric fields. So PDOT is a wonderful material because it doesn't have this deprotonation happening. Also, the positions of 3 and 4 on the ring are protected, and that increases stability. So it's a commercially available, stable material that we like a lot. There are better performers. Ian McCulloch has synthesized the material which is 10 times better in OECTs, but PDOT is in the clinic, and it's very hard to beat this. It's very difficult to take a new material and take it all the way to the clinic. That's why a lot of our work is still with PDOT.
Mm-hmm. And how about the nanostructure?
Nanostructure, yes. So if you think about volumetric capacitance as ions going into the volume of the film, we find that they distribute quite uniformly down to voxels of the order of micron cube. So this points to treating the material like a slab, and increasing porosity is not going to help dramatically. That was my thinking until fairly recently, when Dion Kodagoli came up with this concept where you create ion pockets inside the channel. I think that merits looking into nanostructured morphologies where you can create well-defined ion reservoirs within the material. So I expect that to be an area of high interest in the next few years.
Well, thank you so much for explanation and answering. Thank you.
You're very welcome.
Hello, George.
Hi.
It's a very nice talk, and as always. So thanks. Also, you answered the questions for the previous two researchers has been asking. So I actually pretty much you answered pretty much my question but I have one follow up. So especially using the P-dot PSS as the volumetric capacitor, so then you have the charge transport involved when the device are working. So when you do utilize this as say OECT device, so what about the frequency or sampling rate you're mostly can achieve?
Yes. So with P-dot PSS, you can push. Where is it? Let me go back to the slide. So yeah, right here. So here you can start pushing at kilohertz with a transconductance in the single digits of millisiemens, which is not bad. And you could push even further by making the film thinner. You're gonna lose a bit of transconductance, but by using these ion pockets inside the film, then you can extend the frequency range by, I think, 2 orders of magnitude for the same transconductance. This is a back of the envelope calculation that I'm mentally doing as we speak. You can look into this work by Dion Kodagoli for exact figures, but you have enough range in terms of frequency for capturing the fastest neural activities that you can care for. in the past, there was a criticism that, oh, you need to drop your transconductance to very low levels in order to extend the frequency range. That has been alleviated by this work.
Thank you, George.
Cheers.
Are there any other questions people want to talk to George? There are a couple questions in the Q&A. We can go over those, but if you want to ask George a question live, please raise your hand right now.
I have a quick one, if that's okay.
Go ahead. Go ahead.
Yeah. So regarding the OECTs and using them for sensing, can they amplify voltages and currents, or are they only amplifying voltages? Like, what kind of sensing modes can you use them for? And I guess more generally, what other applications could you imagine them amplifying some of these electronic signals?
Yes, so for neural applications, they're basically very similar to electrodes. They detect the exact same thing. So the interface between P.PSS and the cerebrospinal fluid, you would temporarily set up an electric potential difference that then will drive ions in and out of the semiconductor. And that in an electrode will be translated to a voltage measurement. In the transistor will be translated to a change in the current. That in the transistor you have amplification in the power of the signal, but you are measuring the exact same thing. So at the end of the day, it becomes philosophical whether you're measuring the current or the voltage. If you look just at the interface between the semiconductor and the electrolyte, if you have a small voltage drop there, that's going to lead to a current that will be transduced, or vice versa. If you pump in a current, that will be again transduced. It will be the equivalent of having a small voltage drop at that interface.
Understood. Thank you.
So there's a question in Q&A. Hugo King Oakley asked, which area of your lab's work are you most excited about?
Yeah, so currently the biggest project that we have is trying to develop the ion pump for delivering chemotherapy. And this is down the road, I see this as a major area of development for bioelectronics, where you're going to address tumors not only chemically, but also electrically. There's already some work there under the umbrella of what is called tumor treating fields, or irreversible electrophoresis. Electrophoresis, where people electrophoration, where people are using electric fields, either AC or pulsed, to basically kill cancerous cells or affect their proliferation. This has been decoupled to bioelectronics, and people with a background in electrophysiology haven't been involved in this field. So as a result, it kind of developed as a separate community. I think there's going to be a lot of cross-fertilization there from the cancer community, from the brain cancer community. I hear very strong calls for people with neuroengineering background to get involved. So I think the planets are aligned, and it's going to be a really nice domain for future application. And another project is what I've shown in the last few slides, is the devices that can deploy through minimally invasive surgery. That's a very practical problem, but I think it can be a fairly significant application.
Thank you so much, George, for the wonderful presentation and for answering all these questions. Thank you, everyone, for coming here to join us. Hopefully, everyone really enjoying this despite some bumps at the beginning as we overload. Thank you, George, for such a popular and wonderful talk. Yeah.
Thank you. Thank you very much.